मंदोकृपद्गंज कृपा सिंधुनरूपहरि महामोहतं कुञ्जजासुवचन रविकरनिकर मंदो सीताराम द्विपद सकल सुमंगल मूल सुनाम भरनो कछुक जो मो पर अनुकूल श्री राम नाम को रसिक जे तिन पद रजमम शीश गणपति हनुमान शुक सनकादिक हीश विधि नारद प्रहलाद कृपा व्यास गटज कविराय लोमश गरुड़ मुशुंडि भृगु यागवल के भरद्वा श्रीवाणी गिरिजादित्य जीव चराचर छोड़ राम नाम जिम सरस पिए तास चरण सिर मोर राम नाम को कही सकै जानि सकै को गाओ यथा सिंधु खग चोचवरी त्रिविध थाह नहीं पाओ। Namaskar everyone. Today we are going to start the course on Siddhant. Siddhant essentially involves itself with understanding the positions of different celestial objects in the sky. It was one of the vibhaga of Jyotisha, which is considered as a Vedanta in Indian tradition. So, Jyotisha being Vedanta, it is the eyes of the Vedas. It is a Pratyaksha Shastra and it helps us know about how things are happening, why things are happening, and how things are happening. So, a very, very important thing about Jyotisha is, of course, Siddhanta. Siddhanta, because you will analyze things only after you have calculated the position of different things in the sky. So, there's a very rich history, of course. There is the Surya Siddhanta, which in the current form doesn't seem to be the actual Surya Siddhanta. The one that Burgess actually got access on, translated, and thereafter others have written detailed commentaries on. But we'll take that as one of the major texts for this course. Then, of course, there is the famous Aryabhatiya by Aryabhatta, which I consider as the crown jewel of Siddhanta when it comes to the Indian Siddhantic literature. Additionally, you have different works by Brahmagupta, by Bhaskaracharya, and the Kerala astrologers, including Nilakanta, Somayaji, Nilakanta Somayaji, and others. So, all of them, very long back ago, had developed a very, very sharp, detailed, and accurate model on how to figure out the night sky just by looking at the sky and by doing some detailed calculations. Those calculations are very intricate, and the calculation that you get from Siddhanta was always supposed to match the sky that you see in front of you. So it was not a theoretical exercise. We also find similar exercises being done by Ptolemy and other astrologers in the West. So India, it had a much more expansive, expanded, and detailed framework. The framework finds its pinnacle in the works of the Kerala school. And in this course, we are going to understand all of it mathematically. What my task in this course would be to explain Siddhanta through different schools and the gradation that it has gone through while bringing to life the mathematics that is implicit in the entire Siddhanta architecture. If the yuga man has been considered, if a particular number has been given to the yugas, and if a particular number has anywhere been given, why has that number actually been given? What is the hidden mathematics that is beautifully lying there? So this is what I've been working for the past about 1 year to understand Siddhanta properly. And now I'm going to share whatever I could learn with all of you in the hope that more people would be interested in learning more about it. So when we look at the stars on a clear night, we have, this very familiar scene that we all have seen, which is sparkling points of lights, the stars, some less sparkling point of lights. they are visible in the night sky, and they seem like they are situated on the surface of a big sphere. So if you think about it, it seems like we are at the center of the sphere and there are things on the surface of the sphere that we are looking at. Of course, our eyes cannot give us any indication about the distance at which those particular objects are. It is not possible to find the distance of those particular objects simply observationally. However, if we have to look at the sky, and if I actually imagine like this, that this is a great sphere, I am lying in the center of the sphere, there are of course ways to understand the angle subtended at me, considering me at the point at which the angle is subtended by two different celestial bodies in the sky. Okay, and then when we slowly advance it, we get to know a fairly rich idea about the position of the stars and other bodies in the sky, and also a fairly rich idea about how the change will happen over the next few nights or few years or few decades. We can get that. So the task here is to correctly identify the longitudes of the planets and the latitudes of the planet. Now we'll be covering what exactly I mean by longitudes of the planets and the latitudes of planet, but think of it similarly. The Earth, when it is considered as a sphere, how do we navigate the Earth? We navigate the Earth through lines of latitude, which are essentially parallel to equator, equator being the central latitude point, and lines of longitudes, which basically are from pole to pole. And right now, the central meridian is considered to be Greenwich, the Greenwich laboratory, and therefore it is called the Greenwich Mean Time. In India, in the ancient times, that central meridian was supposed to pass through Ujjain. Okay, passing through Ujjain and meeting up to equator. And that equator point on which the Ujjain longitude actually meets was called Lanka. Please understand that the Lanka of Siddhanta is different from the Lanka of Ramayana. Some so-called modern scholars have gone to the extent of saying that Lanka of Ramayana is not the Sri Lanka of the current times. They're absolutely wrong. The word Lanka here used in terms of equator is very different. It is not Sri Lanka. Please remember that the Lanka of Siddhanta is different from the Lanka of Ramayana. There are many ways that this course could have been done. What I have decided is I have decided to use all modern mathematical terminology. So while I'll keep giving you an idea of the different terms that the Siddhanta uses, for example, jya, etc., I will also ensure that you understand the language that is relevant to us, that we have all become used to in the course of our studies. Okay. And there was another choice that had to be made, whether I wanted it to be plain scalar geometry or I wanted to get some vector input to it. I have decided that we will do a little bit of vector algebra, linear algebra. We'll integrate it with the study of the course, because linear algebra, when integrated properly in a course of astronomy, gives the kind of rich insights which are not possible to get otherwise. So essentially, what we are going to do today is to work through the mathematical basics, and this will continue for 6 lectures. This is happening because I have decided to slow down the pace of mathematical introduction. The earlier plan was much more aggressive. The entire plan of part 1 has now been split into 6 parts. So without much ado, let us get into the presentation and try to understand this beautiful concept. I hope that the slide is available. Can I get a thumbs up if the slide is visible? Perfect. So today I want to build a bridge from something most of us have already seen in physics to the geometry we need for spherical astronomy. We'll begin with vectors, especially the dot product and the cross product. Then we'll place those vectors inside a sphere. Once we do that, great circles, poles, meridians, and spherical triangles, these are the terms that you will keep coming to throughout this course, will begin to fall into place almost by themselves. The important thing today is not to try and memorize formula or even understand the derivations. We are going to do stuff which will challenge your intuition, because one of the core rules of plane trigonometry is that the total sum of triangles cannot be more than 180 degrees. Right? The total sum of the angles, three angles of a triangle, cannot be more than 180 degrees. For our purposes, almost all the triangles that we are going to use will have the total sum of angles subtended at the corners as more than 180. It is not something new. It was known to the Indians many years back. There was a very developed field of mathematics called spherical trigonometry, which used to be taught in almost all mathematics and engineering classes till the 1950s, after which it surprisingly vanished from the main course, but that does not take away from the utility that it has. For our purposes, the utility is absolute. So we'll begin by understanding it in the language of vectors. You don't find this typical classification elsewhere. In doing my work, I found it useful, therefore I have formalized it. For general understanding, the best book to understand spherical astronomy and spherical trigonometry is the book by W.M. Smart. This is the book. I recommend that you buy this book, textbook on spherical astronomy, 6th edition by W.M. Smart with a revision by R.M. Green. But what we are going to talk here mathematically will be different. So all the derivations and all, you'll find it to be different. I've tried to modernize it even further. So the important thing, like I said, is not to try and understand completely or memorize. It is to allow things to settle in your mind. Then slowly as we move ahead, everything would have become very, very clear in your minds going forward. There will be no confusion. But for now, we must go through this process. Imagine a sphere, a plane. Imagine now a plane crossing through the center of a sphere. A sphere can be any ball. Think of the center of that sphere. Imagine a cut right across the center. Now a plane has been created. The plane gives us the great circle. What I mean, you imagine a plane crossing through the sphere, then the circle that is now created on the surface of the sphere, that is called as a great circle. So what is the definition of the great circle? The definition of the great circle is that it gives us, it is a circle that passes, that is there on the surface of the sphere, and which, if extended into a plane, passes through the center of the sphere. Okay. So that is one part. One is a plane through the center of the sphere, and then imagine a line perpendicular to that plane. The plane gives us a great circle, and the perpendicular line gives us the two poles. The pole has to be always defined with respect to a great circle. For example, in the case of Earth, what we describe as the great pole is essentially the equator, from the point of view of equator. So equator, like you see, is a plane that passes through the center of the Earth. Okay, the circle which is there on the surface of the Earth, which is subtended by that plane, is called equator. Okay, now if I draw a line perpendicular to that particular plane that has been subtended through the center, that perpendicular line gives me the poles, the North Pole and the South Pole. Okay, I hope this is very, very clear now. So what else? What after that? So what we are going to do is, first, we will prove that two independent vectors from the same origin determine the plane. This you already know. Two independent vectors from the same origin. Okay. So essentially you consider a point. Two vectors means two lines with an arrow. No matter where you draw the second line, you can always create a plane. So that is a normal geometric intuition which anyone with basic mathematics has. But we will still show it. Okay. Second, 2 points on a sphere normally determine one great circle. You take any 2 points on a sphere, you will be able to draw a plane through them via the center. There are two exceptional cases. One is when the points coincide, which means there is just 1 point, not 2 points. Second is when they are exactly opposite to each other. When they are exactly opposite to each other, it is like you have the North Pole and the South Pole. Then you can draw infinite many number of planes, which is all the meridian circles that we have. The third point to understand is that a sphere by itself has no pole, like I mentioned. A pole only appears after we choose an axis, a rotation, or a great circle plane. Fourth, every great circle has a pair of opposite poles. What I mean by that, an antipodal, this relationship works in reverse too. So an antipodal pair can determine the corresponding equatorial circle. And at the end, we will use these ideas to bring our first formula of spherical trigonometry. So enough of the basics, enough of the build-up, the formulaic build-up. Now let us start the presentation again and see through it slide by slide. Is it visible again? A thumbs up, please. Good. Okay. So first thing is, of course, I have tried to give you the basic definition of the products. Okay. And I want you to separate two operators because they are easy to mix up. The dot product and the cross product. The only commonality between them is both of them take two vectors as input. However, the results that they lead to are very different. They essentially give solutions to different problems. The dot products, it talks about the angle between the directions, the two directions in which the vectors are going. It talks about the angles between the direction, while the cross product, it tells you about the plane containing these directions. And this distinction is essentially the backbone for the entire Siddhanta course that we are doing. Dot is for angular separation. Cross is for the carrying plane. Look first at the dot product. So here you see that there is a modular sign here. So it gives you a scalar result. Sorry for this. This will give you a vector result. Ultimately, there should be vector here. So the dot product gives you a scalar result. A scalar result means it's a number. There is no direction that is associated to it. Okay. For two unit vectors, the dot product is simply the cosine of the angle between them. The cross product gives us a vector and its direction is perpendicular to both the original vectors. So it points perpendicular to the plane that they span. That is why these two operations, they complement each other so well. Why? The magnitude of the cross product, it contains information about the angle, while the direction tells us which plane we are talking about. The fact that the cross product returns a direction is what will let us identify a great circle plane, and that is why I have decided to use it for the purposes of our course. So first is dot product. Like I said, there are two vectors that you see here. The two vectors are A and B. Okay. The two vectors are A and B. So this is first vector. This is second vector. And how do we define the product? We define the product very simply as, just 1 minute. 1 minute, please. Yeah. So consider that the length of both of them is 1 for now. Let us consider equal length. So normally the dot product is the product of these two lengths times the cosine of the included angle. Now, if we consider the lengths are equal, the formula simply becomes cos theta. There is nothing more because A and B, if you consider both of them to equal, it simply becomes cos theta. Now, if I know the two direction vectors, I take their dot product and then I take the inverse cosine. That will essentially give me the angular separation data. Or even if these numbers are there, I'll simply take A dot B by A mod B mod, and I'll take the inverse of that particular value. That the inverse of that particular value will give me. This inverse is most very easy to understand in case it is very simply unit vector or same vector. On a sphere, an angle at the center immediately gives you an arc length. An angle at the center. So any point, you take one point on the surface of the sphere, drop it to the center, another point on the surface of sphere, drop it to the center. Okay. So what have you done? You have got an angular separation. For example, I have given you an example. Paris and Mumbai. If you do this angular separation, the angular separation is about 63.04 degrees. Which corresponds to about 7,009 kilometers. So this angular separation is one of the basic measurements that we can do. So this is the arc that Mumbai to Paris will cover. Now you can calculate it yourself and you'll be able to get the idea of how beautifully you will be able to take it. Okay. And since you can consider the A and B to be unit vectors, both the points to be equidistant from the center. We are imagining right now that the sphere is a perfect sphere, not an oblate spheroid. If it is a perfect sphere, not an oblate spheroid, we can clearly find the angular separation in terms of both the degree and the arc. So if I have the arc length, I can find the degree. If I have the degree length, I can find the arc. Now let us come to cross product. What is cross product? Think something like torque. So those of you who have done torque is basically R cross F. So why does only the perpendicular component of the force turn the object? Because the cross product gives us the direction. The torque vector points perpendicular to the plane containing R and F. And you have to use the right hand rule to find out the direction. If you have ever used a screwdriver or anything, then the right hand rule is very necessary. If I am going to screw in that direction, then I have to screw in this fashion, because this is how the nail will go in. If I am doing this side, I have to screw in this fashion. This is how the nail is going in. So direction is given by the right hand rule when it comes to the cross product of the vector. And we are going to use precisely the same idea on the sphere. If two radius vectors, they lie in a plane, their cross products therefore points perpendicular to that plane. So what we have done, nothing new. We are just saying 2 points going to the center, a plane being subtended, the cross product will go out perpendicular to the plane, depending on the direction that you take. Here to here, if you decide here to here, the plane will be, the perpendicular will be outside. If you decide here to here, it will be in the other direction. So this is what the cross product is. Don't think too much about how geometry and all match. They will match. Ultimately, will match everything. If nothing else, will force fit. So don't worry about it. So next is the parallelogram rule. The parallelogram rule basically, y is the magnitude product contains sine theta. Okay. So draw the parallelogram made by two vectors. And what is the area of the parallelogram? The area of the parallelogram here is very simple. Base times the height of the perpendicular. Base times the height of the perpendicular. Now, if the base has length magnitude A, the perpendicular height contributed by B is basically B times sine theta. We all know what is sine. Some people have perpendicular by hypotenuse. So this is the hypotenuse. This is the perpendicular. Since this is B, this height essentially becomes B sine theta. Okay, I hope it is all clear to everyone. This is all revision of basic mathematics, so should not actually be a problem. Now notice what happens if the vectors become collinear. If the vector becomes collinear, what will happen? The parallelogram flattens and the area becomes 0. What do I mean by vectors becoming collinear? So suppose I decrease the angle of B here. I decrease the angle of B further. I decrease the angle between A and B further. And finally, A and B are together here. Once this happens, it basically means that the product returns to 0. Why? What is sine 0? Sine 0 is 0, right? So because sine 0 is 0, here this will become 0. This is necessary because we'll derive from it. I have told you something. You get an idea about a particular method. We will simply implement it into spherical trigonometry and derive a result going forward. These are the three most important angles in trigonometry, so as in spherical trigonometry. So at 0 degree, the vectors point in the same direction. A dot B will be +1 and A cross B will be 0. Just like the parallelogram example that we talked about. At 90 degrees, the dot product is 0 and the cross product magnitude is 1. At 180 degrees, the vectors point in exactly opposite direction. The dot product is -1, but the cross product is exactly 0. So a 0 cross product, it does not tell us whether the vectors point together or opposite to each other. It simply tells us that they are collinear. The dot product, it distinguishes the two cases. Okay. Now, going forward, sorry. Yeah, going forward, the order matters. So what you can see here is there are two different points that we have considered. Since this is a two-dimensional thing, it may be difficult to understand, but just think of it like this. This is like a great circle that we talked about. This is the sphere. This entire thing is a sphere. This is the center. This is something like an equator to Earth. Okay. Now, this is the surface. This entire line is on the surface of the sphere. That gives you the idea of the three-dimensionality here. This is one vector coming out here. This is another vector coming out here. So like I mentioned, depending on where you are looking at, that is the sign convention. A cross B is the negative of B cross A. Reverse the order and the normal points the other way. So this is B cross A coming here. This is A cross B going there. This is just my attempt to show in the language of spherical trigonometry how cross point direction, cross product directions operate. So the plane has not really changed. The plane remains the same. However, the plane has two opposite normal directions. So both cross products, they identify the same plane and therefore the same great circle. For simply counting great circles, this sign does not matter. However, for directed astronomy, signs do matter. We therefore chose an orientation convention and keep it consistent. Okay. The important point here is opposite normal, but the same plane. Now we need to move from the vectors to the sphere. So imagine the common origin of our vectors is the center of a sphere. This is what we have been talking about. The tips of the radius vectors are points on the sphere. What we just discussed in this slide, the tips of these two radius vectors are points on the sphere. Okay. Now the question that we need to answer now is, given 2 points on the sphere, how many great circles can pass through both? Everything that we have just done with the dot and cross product is enough to answer that. So from 2 radius vector to 1 great plane. Okay. what do I mean by this? I'm sorry. Yeah. So, sorry guys, my system is getting stuck up a bit. Yeah, now it is fine. So, what am I saying? If I have two radius vectors, I have to know how many great center points. So let A and B here be the points on the sphere. A and B are the points on the sphere. Let O be the center. Draw two vectors A and B. Okay. Now, what do I get? N cross B, the radius vector. We call the radius vector, say, a small a and small b. So this hat gives you an idea that it is a vector. We're using the vector terminology. Now, if a cross b is not 0, it gives one definite normal direction n. So only in case a dot b is 0 can this thing completely go away. Can I not get a direction? Okay. Once I know a normal and I insist that the plane passes through 0, the plane is fixed. There is only one such plane. The plane cuts the sphere in a great circle. Therefore, two distinct non-antipodal points determine one great circle. Now, look carefully at the normal in the diagram. It rises out of the plane. We drew it as though it lay inside the plane, but it is actually rising out of the plane. So this is the sphere. There is a plane inside and the vector is rising up. Okay. This rising vector will tell you the pole for this great sphere. The upper vector will be north or south pole depending on the direction. And when you push it, that will be the other plane. Okay. Now, going forward the same way, there is some definition like I defined. This is a sphere. Any circle that goes through this on the surface, it's a great circle. Now, this great circle could also have been drawn like this. And then this is also possible. So just the fact that I have made it completely perpendicular to this line doesn't matter anything. In this case, this is how the pole would have been. Okay. So this great sphere, this great circle that we are talking about, this great circle essentially means that it passes through this. Now there are small circles. In small circles, it can be any plane similarly, but it doesn't pass through the center. That is the core idea. It doesn't pass through the center. This is all that we have to remember. What is meant by a great small circle and a small circle. So this is why the equator is a great circle, while the Tropic of Cancer or the Tropic of Cancer or the Arctic Circle or the Antarctic Circle, they are actually small circles, because all those other circles that I talked about, the latitudes, they do not cross through the center of the Earth. So between two non-antipodal points, the unique shortest path on the surface is the minor arc of their great circle. Between two, the unique shortest part of the surface is the minor arc. So suppose I consider these 2 points, A and B. Okay. This I can define as the minor arc. So that is what is defined as the minor arc. This is the unique shortest point on the surface. Now for antipodal points, that is points on the other side, the distance is still definite, but there are infinitely many equally short circumference. What do I mean by antipodal point? These 2 points are antipodal. Okay, any point which can be drawn as a perpendicular to a great circle. Now if I consider these 2 points, then infinitely many planes can be drawn passing through the circle. This is one plane. This is another plane. This is another plane. And this is what we know as meridians of longitude on Earth. If we look at it in terms of Earth, these are meridians of longitude. So what did we say? We said that a sphere, a circle on a sphere is called a great circle or a small circle according to where the cutting plane lies. If the plane passes through the center O, the circle has the same radius as the sphere, that is a great circle. If the plane misses the center, then it is a small circle. That is why equator is a great circle, while every other parallel of latitude is a small circle. Between two non-antipodal points, the unique shortest path on the surface is called the minor arc of the great circle. And for antipodal points, there are infinitely many short semicircular routes that are available, which are the shortest point. And then the complete circle, the number of planes also can accordingly be infinite. I hope till now all of us are clear. Now we go to the plane equation. What is the plane equation? This is the same idea that we discussed before, which is written as linear algebra. A plane through the center can be described by a normal vector n. Every vector x lying in that plane satisfies n dot x equals 0. Because why this is so? Because x is perpendicular to n. Therefore, every vector lying on the plane, it satisfies n dot x equals 0. What do I mean by every vector lying on the plane? See, this is one vector. This could be another vector. There can be infinitely many vectors that can lie on this plane depending on which point on Earth I want to focus on. Are you getting me? Okay. So, what I just said, that every vector lying in the plane is perpendicular to the normal. This is the plane equation. N dot x equal to 0. Okay. If the plane must contain both A and B, then n dot A equals 0 and n dot B equals 0. So no matter how many vectors you actually do, the polar line, the polar vector, which is determined by the cross product, will make sure that the dot with the polar vector of the actual vector is always 0, because that is 90 degree. And what is the cos of 90 degree? Cos of 90 degrees is 0. Therefore, this must be 0. Now, when A and B are independent, these are two independent conditions on the three components of n. Therefore, the possible normals, they lie along one line, and that line is the cross product direction. One normal axis basically means one plane. Every plane passing through the center will have one normal. Every other plane also will have one normal axis if you consider the center. If you what can be done there, a center can be imagined, and from there you can do that. At times, the smaller circle, if you make it parallel to the larger circle like we have done here, then we can identify a center here, and from this center we can have the curve, and their directions will be same. Are you seeing that? So this can very simply be done this way. And when one radius vector is a multiple of the other, the two conditions are linearly dependent. Only one independent condition remains. A whole plane of possible normal is what will survive. So infinitely many carrying planes are possible when one radius vector is a multiple of the other, which basically means that they are coterminous to each other. They are linearly dependent to each other. Now, first is the case of distinct antipodal points. This is the ordinary case. O, A, and B are not on one straight line. These are three non-collinear points on the plane. Why do I say non-collinear? Because they are not in a line, right? These three are not in a line. Therefore, we call it these three non-collinear points. Now the cross product is non-zero. So the normal direction is unique up to the sign. And the normal axis determines one plane through O, and that plane cuts one great circle. This is that one great circle that we have been able to cut. So no matter where you keep it, if they are antipodal, yeah, if they are non-antipodal, I described non-antipodal, which are not parts of the same pole that is going through the center. If they are non-antipodal and two non-collinear points, it will determine one plane. So the third non-collinear point will be the center of the sphere itself. The heavy arc shown here, which you see like this, you find that this is where the shorter route from A to B is. This is the shorter route. What did we define the shorter route as? We defined the shorter route as the arc. The arc, that is the small arc that is covered by the minor arc. The minor arc which is covered, and we find which is the smallest direction. So this arc is called the minor arc of the great circle, which is formed by these two non-antipodal points on a sphere. Okay, so we took the example of theta equal to 65.51 degree. This is what we had done there, the shortest path from Paris to Mumbai. Now this is the case 2. The case 2 is opposite hemispheres, but still one circle. In the case 1, it was the same hemisphere. So it was the same hemisphere. Consider it is north and south. I am not say this is the hemisphere line. Okay, this is north hemisphere, this is south. So even then it was possible. Now even if they are in the different hemispheres, even then nothing changes. Now put one point north of equator, put one point south of equator, nothing changes in the count. They still determine exactly one great circle. And this is useful because it is possible when learning spherical trigonometry to start thinking in terms of hemispheres. Same hemisphere, opposite hemisphere, north, south. None of that decides the number of great circles. The only question is whether A, O, B, and A, they are collinear or not. If they are collinear, it will not happen. When they are collinear, when they are antipodal. When they are not antipodal, they are not collinear. Simple. The hollow point marked -A shows where B would have to be for the geometry to become exception. Here, अगर B यहाँ पे होता तो भाई कोई भी हमारे मल्टीपल सर्कल्स बन सकते थे, क्योंकि ये एंटीपोडल हो जाता. For it to become antipodal, we would have to define -A. If -A is not defined, B is very far from it. Therefore, we are nowhere close to that situation. Now is the point for case 3. These are the antipodal points. Okay. Now, B is exactly -A. This is A. This is A minus A. So now B is equal to -A. Since this is the case, now there are infinitely many planes that can pass. The two radius vectors now lie on one straight line to O, and they do not span a genuine plane. Imagine a sheet of paper hinged along a diameter A4 prime. The sheet can rotate freely around that line. Every position of the sheet is a different plane through O, A and A prime. बीच में एक पन्ना लगा के उसको घुमा लो, हर पॉइंट जो है वो एक प्लेन बना लो. Okay. Similarly, each of these planes, they cut the sphere in different great circles. That is why the cross product becomes 0 here. 0 doesn't mean that there is no plane. It means that there is no unique plane which is selected by the pair. Please keep this point very, very clear. Now, इसी को हमने axis के नीचे से देखा. If we is the same antipodal case that's seen directly down the diameter A4 prime, जैसे हम बोल रहे थे. So every plane in the family is now seen edge on. So each appears as a straight diameter. नीचे से देखोगे तो हर plane एक straight diameter की तरह दिखेगा. So as the plane rotates around the common axis, these diameters will sweep continuously through the figure, and there is no preferred member of the family. Now, this picture actually helps make infinity very concrete. We have not merely found several great circles through the antipodal pair. We can rotate continuously and obtain another one at every angle, sub-angle, sub-angle. You can go as close. You can make the delta as small as you like to. It will still remain. Now, we can understand the same result from the normals. When A and B are opposite, A cross B is 0. The 0 vector has no direction. So the cross product cannot choose a unique norm. Now, which normals are allowed here? Please, the same thing we are looking at different ways just to understand it. Because this is the part that I found most difficult on intuition. Therefore, I am focusing so much time on it so that this intuition is not missed at any point in time. So, which normals are allowed? Every direction perpendicular to the diameter. Now, if you restrict these possible normals to unit length, their tips form the red circle shown here. यहाँ unit पकड़ लो अगर सारे का तो यहाँ पे ये एक red circle तुम्हें बनता हुआ दिखेगा. ठीक है? Now, what does that mean? Each arrow on that circle is the normal to a different plane, and each plane gives a different grade circle. So same point again. In the antipodal case, we have an entire circle of possible normal directions. वहाँ पे एक plane, एक normal direction. Here we have an entire circle of many possible normal directions. Now, why the count changes? So the entire distinction can be stated as a question of how many independent conditions we have. तो हमको जवाब मिल जाएगा. We want n to be perpendicular to both radius vectors. Both radius vectors. And for an ordinary pair, A and B are independent. That gives two independent conditions. In 3 dimensions, the solutions for n are reduced to one line, one normal axis, one plane, one grade circle. If one vector is a multiple of the other, there is only one independent condition. I hope I am making it very clear. This is, like I said, the basics we are just covering. But we are covering it in 3 dimensions. So you'll have to use your imagination. And the possible normals, they form a plane instead of a line. Hence, infinitely many circles. On the sphere, there are only 2 ways this happens. The 2 points are same or they are antipodal. Yani kya? If 2 points are not exactly opposite each other on the sphere, passing through the center, okay, then any 2 unique points on the surface of the sphere will give you exactly one big circle. That is the only point that you have to remember. Okay. Now these are some of the computed values. What we have computed, this table puts the numbers behind the geometry we have developed. For the first 3 pairs, you see the cross product magnitude is non-zero. You see, they are all non-zero. The last one is actually Mumbai and Paris. Okay. आपको यहाँ पे ये non-zero cross products मिल रहा है. And for the antipodal example, here we have gone the antipodal example where it is 180 degrees apart. You find that cross product is 0 and there are infinitely many planes possible. Similarly with Mumbai and antipod and ANA itself. So Mumbai to Paris, it runs 7,009.3 kilometers along its great circle. Mumbai to its antipod will run 20,015 kilometers along any of the infinitely many semicircles. So I have done this calculation. You can verify this calculation. It is very simple. No big mathematics. You can use a trigonometry table and very easily do it, or you can do it on Excel. Okay, now we'll put the same test on the celestial sphere. This is where I will explain things a little bit before going forward. So we'll go into the celestial sphere tomorrow. I hope that you have been able to figure out the geometry that we are trying to do. Okay, the geometry is very clear. We understand the sphere, the great circle, the small circle. Tomorrow, we will build on how the great circle and the small circle can be understood in terms of celestial sphere. See, we will continue talking about two spheres when we talk Siddhanta. One is the Earth itself. So we'll consider a person stationed somewhere looking at a star. He can be stationed at the equator. He can be stationed at any point anywhere of the Earth. How does his position change things in terms of how the stars appear, where the stars appear, etc.? How long the signs take to rise, how whether the rising and setting is happening uniformly or at different speeds, whether the signs rise and set uniformly, whether the planets rise and set uniformly. So all of these things we can understand. We will consider Earth as a sphere when doing some calculations about seasons, about equinoxes, about eclipses. The second is the celestial sphere, wherein we will assume Earth to be the center of this sphere. And we expand it. It is just the frame of reference. We are not changing. We're not saying that this is a geocentric universe. No, it is not. But in physics, those of you who have studied it, the frame of reference will be. What is my frame of reference? I am watching from Earth as the frame of reference. Since I am watching from Earth as the frame of reference, everything appears like a sphere. Then for observational astronomy, it makes a lot of bloody good sense to make sure that I look up directly in the sky, imagine that sphere and start calculating. So we'll be using two different spheres during the course of our lectures. And for both these spheres, we'll have the use of the big spheres and the small spheres and the mathematics that comes from. So this is where I'll close today. We'll meet again tomorrow. The time has been given. Any questions you can put on the Telegram group. This video should be available on YouTube, hopefully by tomorrow. That's all from my side. Namaskar.